For problem number 5, we have a polar equation and we need to express it in Cartesian notation. So our polar equation is r equals 2 cosine theta. So there's two ways to approach this problem, and I'll do it both ways. First way, which I think is a bit simpler, is requires you to know what this graph looks like, and then you can just go to Cartesian there. So remember that if you have r equals any constant times theta, or any constant times cosine theta, you're going to get a circle that has its leftmost point on the origin. And its radius is always half of this constant. So its radius is 1, so that must mean it's a circle that goes to 2 from the origin. So we just have a circle over here in the right half of the graph. Its center is right here at the point 1, 0. So you can see here, if you know what the graph looks like, making a Cartesian equation to match this graph is pretty simple because you know the center and radius already. So as long as you remember that the equation for a circle, x minus h squared plus y minus k squared equals r squared, hk is the coordinates of the center and r is the radius, we have all that information. So that would just be x minus 1 squared plus y squared equals 1. Because our y coordinate of our center was 0, our x coordinate was 1, and our radius is 1. So the other way you can do that is just use the Cartesian to polar transformations. So remember that those are r is equal to the square root of x squared plus y squared. Cosine theta is x over r, and sine theta is y over r. You might have seen those a little bit differently. X equals r cosine, y equals r sine, but it doesn't matter. Those are just rearranging the same thing. So it's the best way to do that is to do it kind of in stages, because if you get r squared, that's actually useful because you already got rid of the root then. So what I'm getting at is you want to substitute for the cosine first and then deal with the r at the end. So this is the same thing as saying r is equal to 2x over r. Therefore, we're saying r squared equals 2x. And now I can just substitute r squared is x squared plus y squared. I don't have to deal with the radical anymore. So now I have a purely Cartesian equation, and I can rearrange that to get in the form of a circle. Now this is going to involve completing the square, if you remember from like pre-calculus. So what I have to do here is say x squared minus 2x. I'm leaving a space on purpose. I don't have to do anything with the y squared because I don't have any y terms. However, since I have x squared minus 2x, I want it to be in this form, so I have to make it a perfect square. And to do that, you take half of this constant here and square it. Half of negative 2 is negative 1. You square that, you get plus 1. So I have to add 1 to both sides of this equation. And you can see then this factors into x minus 1 quantity squared, this whole part right here, plus y squared equals 1. And if you notice, that's the exact same thing I got by just doing it from a graphical approach. So either of these methods is fine to convert from a polar graph to a polar equation to a Cartesian equation. Sometimes you'll get ones where the formula is a little bit too complicated to graph easily. But if it's one that you simply know the graph of in polar, oftentimes it's a better idea to switch that to use the graph to switch it to Cartesian rather than to use all of the formulas.